Today we are going to listen to Dr. Marco Pavone, who is an associate professor of Aeronautics and Astronautics at Stanford University, where he directs the Autonomous System Laboratory and the Center for Automotive Research at Stanford. He also serves as a director of autonomous vehicle research at NVIDIA. Before joining Stanford, he was a research technologist within the Robotics Section and the NASA Jet Propulsion Laboratory. He received a Ph.D. degree in Aeronautics and Astronautics from Massachusetts Institute of Technology in 2010. And his main research interests are in the development of methodologies for the analysis, design, and control of autonomous systems, with an emphasis on self-driving cars, autonomous aerospace vehicles, and future mobility systems. He is a recipient of a number of awards, including a Presidential Early Career Award for Scientists and Engineers from President Barack Obama, an Office of Naval Research Young Investigator Award, a National Science Foundation Early Career Award, a NASA Early Career Faculty Award, and an Early Career Spotlight Award from the Robotics Science and Systems Foundation. He was also identified by the American Society for Engineering Education as one of America's 20 most highly promising investigators under the age of 40. And now we can listen to him.
And unfortunately, I'm no longer under the age of 40. But with that, yeah, happy to be here and happy to see some familiar faces. I also see on Zoom some people that I had the pleasure to interact with at Stanford, like Ravi and Sarah. So happy to be here. So today, what I'm going to talk a little bit about is my research on how to use foundation models to, like, for example, large language models and vision language models to rethink how we develop autonomous systems, and in particular, autonomous vehicles. Now,
We start sharing. I think like you not sharing, right?
I was sharing actually. Yeah, let's see what happens. Yeah, so the premise of my talk is that, of course, generative AI is completely changing the way we work, the way we seek out knowledge. For example, here I'm showing on the left how models can write code for us. And the emergence of such capabilities is so profoundly revolutionary that some people refer to it as the iPhone moment of AI. So it's natural to wonder what has happened in the past couple of years to really power this revolution. And broadly speaking, what has happened is the advent of foundation models, which has shifted us from a paradigm of machine learning for specialized tasks to the paradigm of general knowledge acquisition. Now, I want to be a little bit more specific in terms of what I mean by foundation model. And in particular, following the definition from by the Center for Research on Foundation Models at Stanford, by foundation model, I mean a model that has been trained on raw data, typically at the internet scale and in a self-supervised fashion, and it can be adapted to a wide range of downstream applications. Examples of foundation models include large language models, vision language models, video prediction models, and actually, NVIDIA has a website with a number of foundation models that are ready to use, and you can play interactively with them. Now, we're not quite yet at the level of having one massive model that can consume any data modality, and it can be applied to any possible application. But this general idea of retrain on a diverse data at massive scale and then fine-tuning to specific downstream applications has proven extremely useful, and sometimes it leads to, wow, I didn't even know that this model could do that. So AI makes everything better, you might say, and generative AI in particular makes everything better. So let's just apply it to the field of autonomous vehicles. Well, not so fast. I think it is important for us to understand how foundation models can actually help with the AV development. We don't just want to jump on the bandwagon because there is a lot of hype about foundation models. And in that context, it's important to recognize, well, you know very well, that the AV technology is already quite mature and indeed quite reliable. For example, in the context of ADAS systems, advanced driver assistance systems that are being productized as we speak, And of course, remarkable progress has been made even in the context of full autonomy by Waymo, Nuro, Dux, and other companies as well. And this has been powered by the judicious incorporation of machine learning models within the AV stack. That said, of course, still current AV stacks miss the mark when exposed to strange situations, like, for example, new deployment domains, like new geographical deployment domains, or new weather conditions, optical illusions, like, for example, a truck that is carrying some traffic lights. We'll come back to this example later on. And the bottom figure, I don't even know what that is, a giant inflatable minion on a highway. I don't know what is doing that, but it's a real photo. And at this point, it's useful to wonder how humans navigate the long tail of events that you might encounter on the road. And I like to say that typically humans bring in a lifetime of experiences that they have acquired beyond only driving. And this enables humans to display outstanding contextual and semantic reasoning capabilities. Analogously, the research hypothesis, is that foundation models, which have been trained on multiple lifetime of experiences, both from the driving domain, but equally importantly from the non-driving domain, provide an opportunity to bring this outside information to the AV task, thereby hopefully enabling contextual and semantic reasoning capabilities that are really necessary in order to reason about those corner cases. At least this is the hypothesis. Now, the question is how we can access this generalist experience for AV applications. And the answer is in multiple ways. So, as I discussed in the rest of my presentation, foundation models, through their long tail generalization capabilities, can empower several aspects of an AV program, both in terms of offline processes, for example, improving auto-labeling pipelines, simulation, traffic generation, and of course, the online AV stack, for example, by enabling new end-to-end architectures or improving in-cockpit experiences, for example, through conversational AI. So the point here is that even though foundation models are oftentimes discussed in the context of the online stack, I do think that actually they provide a lot of opportunities that go beyond the online stack, with the online stack, of course, a key case in point. Now, of course, safety is paramount, and the common concern is that foundation models might be very difficult to use in a safety-critical context. We are all familiar with, for example, hallucinations. Well, my claim here is that foundation models, at the end of the day, they don't have any black magic in them. They are data-driven models. We have years of experience in terms of deploying and safety certifying data-driven models. So we have several tools to keep them in check. And I will mention this point toward the end of the talk. But I would also claim that foundation models provide opportunities to improve the safety of an AV stack, for example, by enabling the design of new semantic runtime monitors. So what I'll do in the rest of the talk is to give an overview of some of the different use cases I've been investigating in my group. And in some cases, we have encouraging preliminary results. In other cases, we have some hypotheses. That's something that I look forward to discuss in the second part of the meeting today. So since I plan to only talk about 30 minutes, I will only provide some examples from each one of these boxes. And in particular, I will provide one example from the offline process box in the context of traffic simulation. Now, of course, simulation is the holy grail in the field of robotics. And unfortunately, is not as used as much I would like, at least in terms of a full closed loop simulation. And one of the critical challenges is that of properly simulating agents in an interactive fashion. To that extent, in my group, I've done a lot of work in terms of behavioral models that can be used for closed loop evaluation and training. And I think at this point, we are in a good state in terms of achieving a high level of realism, diversity, and controllability for these models. But on the other hand, creating simulations still requires a lot of manual work. So setting up the scenarios, the digital conditions, the different interactions that we want to roll out in order to stress test an NV stack typically requires a lot of work. So here is a setting where foundation models can boost our existing capabilities. Specifically, we have explored how large language models can provide a new and intuitive interface to control the generation of simulation scenarios. In our recent work, LCT Gen, we are able to not only control the evolution, but also the initialization of the simulation scenario via natural language description. So here I'm showing some examples where we start from some initial generated scenario, and then with a language interface, we ask the model to make changes to the scenario. One interesting example is the one here on the right. So basically, we start from this scenario, and then we ask the model to to speed up some of the cars. So look at this blue vehicle. The model decides to place the blue vehicle on the right lane, because if you speed up the cars, the blue vehicle would have hit the front red car. So basically, this scenario generation process is dynamically informed. So one interesting thing about this tool is that, for example, we can take police reports, like, for example, the police reports that have been collected by NHTSA in the Siren database, and recreate them seamlessly in a simulation, possibly with some variations. Of course, the police reports do not provide all of the information regarding a given scenario. Typically, provide information about the relative speeds of the vehicles and on what lane a vehicle was. Of course, they don't provide information about the map or the surrounding environment. And that's where basically the generation capabilities of the model come into play. Specifically, going a little bit more into the details, the way that the model works is by first converting a given scenario prompt or a police report into a structured representation, an example of which is shown below on the bottom right. And this representation is then taken as an input into a map retrieval framework that selects the best fitting map layout. And then we feed the structured representation along with the map that has been retrieved into a motion generation, which places agents on the map and forecasts their motions for the next 5 seconds. And more details are provided in the paper we presented at Corel recently, but that's basically the secret sauce to generate the scenarios are shown here, for example. These are all real cases that we have been able to recreate in simulation. So basically, by coupling this capability with some research we have done in the context of a neural rendering and a neural simulation of both static and dynamic objects, we can now simultaneously simulate both sensor and human agent behavior in novel and targeted ways. For example, here we can test an AV stack on a long-tail scenario whereby a vehicle shows ignorance of a stop sign. Specifically, in the regional scenario, you can see that the vehicle on the top left stops the stop sign, so that's the ground truth. So what we did through our language interface was to manipulate this object, and now we simulate a scenario whereby there is a car that is not paying attention to a stop sign, and similarly, you can say, I want to simulate a drunk person that is not yielding to me, and so on and so forth. And this is kind of interesting because, of course, the sim to real gap here is arguably quite reduced with respect to what we could do just a couple of years ago, both in terms of sensor simulation and in terms of traffic simulation, and the interface is quite seamless. So we are quite excited about this work. But let's move on to actual applications to the on-vehicle AV stack. That is probably what people are very excited about. So, as I mentioned at the beginning, foundation models hold the promise to allow us to drive better through better generalization capabilities. At least this is the hypothesis. But do we have any evidence for that? So to answer this question, we have done some preliminary studies where we have tried to use large language models and the vision language models for the tasks of driving. For example, on the left, I show one of our recent works referred to as Agent Driver, which treats large language models as embodied agents that loosely replicate how humans drive, for example, leveraging capabilities such as detection and tracking, reasoning. So here, basically, what the large language model does is to act as an orchestrator that calls on-demand neural modules, for example, tracking or detection, a cognitive memory, storing basically previous experiences, and then finally decide what to do at the level of a reference trajectory. So it's basically the idea of using large language model as orchestrator through a text interface, which is quite general. It's not like, that was not like the novelty of this work. Novelty of this work was to use this idea in the context of driving. And what is interesting is that when you compare performance with respect to UniAD, which is one of the state-of-the-art academic models, was the winner of the CPR Best Paper Award last year, we can achieve a better performance with 1% of the data that was used to train UniAD. Now, there is no black magic here. The reason why we can use much less specific data is because through the language model, we can bring in a lot of generalist experience from pre-training. And we also had a similar encouraging results by using vision language models. Now, I refer to these works as science papers in the sense that we don't really address a key considerations such, for example, speed. Large language models are notoriously large models, and they're autoregressive models that is really bad when in the context of real-time applications. They're slow and bulky. And yeah.
A very short question about the previous slide.
Yes.
About this image at the bottom right. I think like the original paper for both, at least on archive, we didn't have this diagram.
No, this is not in the paper yet. We should have played the archive. Yeah, it came afterwards. Yeah.
Okay.
But basically, what is shown is that on some metrics that are used, for example, in order to measure the accuracy of explanation and so on and so forth, this model does well. And the main novelty of this model was to introduce a new chain of thought strategy that basically forces the model to provide explanations by grounding them into the objects that are seen in images. So there is basically some structure that is enforced in the chain of thought generation process.
It was something that this paper was lacking just because we didn't have like this. I didn't see any like comparisons with any other model, no any tables, no.
Right. But that was just this field is moving so fast that you try to plant a flag early on. Nice. But thank you for the reminder. Actually, yeah, now we have table with comparisons with many state-of-the-art models, and then we will put the revised version on that.
Okay, thank you.
Anyway, so these are still science papers in my mind, in the sense that they show that there is some potential in using these models, but of course, they do not address a lot of key considerations such as speed or safety. And speed is, of course, a key bottleneck. But on the other hand, we're talking about other research group. Unfortunately, at NVIDIA, there is a research group called Efficient AI that does a lot of work on distillation, quantization, pruning methods for large language models. And basically, it turns out that it's quite feasible to shrink down these models to something that is runnable on an embedded computer. So, for example, here, I'm showing the execution of a Llama model on an Odin platform, essentially in real time. So, of course, still more progress needs to be made in this area, but it's not so inconceivable that at least a reduced version of a foundation model can, if you want, be run on a vehicle. Now, we've seen that foundation models, at least conceptually, can improve the task of driving, and at least in terms of speed, they can be run perhaps at a lower frequency, only in order to reason about the most difficult cases. So this motivates us to explore best ways to integrate, to see how we can best integrate them into NVIDIA architecture. Now, the topic of AV architecture has seen a resurgence of interest in the past, I would say, year or so. In the sense that historically, obviously, the most traditional architecture is a very modular architecture whereby you have different modules such as detection, tracking, prediction, planning, control, and so on and so forth. And there are a lot of advantages with this architecture: usability, introspection, explainability, legacy. But of course, it also comes with some disadvantages. Since you have all these modules, you introduce information bottlenecks, at least that actually this architecture cannot be end-to-end optimized. So it has its own disadvantages. So this motivated around 2016, 2017, the investigation of end-to-end architectures. And in the simplest instantiation, end-to-end architectures are monolithic end-to-end architectures, whereby essentially you have a giant neural network that is mapping raw sensor measurements in control. There are some nuances, but this is pretty much the idea. And this architecture has a lot of advantages. It can be optimized end-to-end, so at least theoretically, you might achieve a level of performance that is not possible with modular architectures, but it comes with a lot of disadvantages. Introspection becomes much more difficult, is not really reusable. I mean, you cannot really change specific subcomponents. And of course, building a safety case with such an architecture becomes much more challenging. So I view these two architectures as two ends of the spectrum. Now, in the past couple of years, thanks to advances in differentiable algorithms, new optimization techniques, people have been starting looking at modular, yet end-to-end trainable architectures, whereby you still have some modules, maybe not as many modules as in a traditional modular stack, but maybe a couple of modules or 3 modules, which can then end-to-end optimize. And the idea is to basically leverage the best of both worlds in terms of end-to-end trainability, but at the same time, introspection. So if you buy this idea, now we open up a huge design space, whereby we have to decide essentially 3 design choices. The first one is the choice of modules. Which module do we want to use in a VE stack? The second one is the choice of representations. Do we want to use, for example, semantic PV maps for mapping, or do we want to use a vectorized representation? So more broadly, do we want to use implicit representation or more explicit outputs and passing information between modules? There are all sorts of things, but how do you compare this type of different representations? And of course, and these 2 design considerations have been addressed to some extent in the past, but there's a third design consideration that is much less discussed, at least in academic literature, that is the one of module placement, basically dependency among modules. For example, should the occupancy prediction explicitly depend on motion prediction, or maybe not? And to systematically explore the huge design space that I just mentioned along the 3 dimensions, so that of necessity of a module, placement of a module, and a choice of a representation, in a paper that we will be presenting at the CVPR, we propose a computational graph paradigm to model the task of driving. And given this framework, to reason about the necessity of a given module, we can remove one of the nodes and simply observe the change in driving performance. And similar to reason about module placement and corresponding dependencies, we can change the connectivity of edges. And also, we implemented different edge types between the modules to reflect, for example, the use of implicit versus explicit representation. So this is really an experimental paper where we did a lot of experimentation to try to see whether there is any major trend or any major architecture that emerge as the best possible compromise. And I'm quite excited about this work because it's one of the very first ones to systematically explore the design space for AV architectures.
Like meta research.
What's that?
Like meta research.
Yeah, it's literally meta research. And the end result is interesting, perhaps a little bit surprising even. It turns out that one of the simplest design, at least in our experiments, appear to be the best in terms of both performance and efficiency. I refer to this design as a para-drive, where para stands for parallel. So this architecture essentially entails a transformer that takes multi-camera images as input and produces output in parallel for 4 main tasks, namely mapping, motion prediction, occupancy prediction, and motion planning. And this architecture essentially follows the philosophy of train heavy and infer light. So basically, in offline training, all parallel heads are necessary and crucial, since the co-training of the different heads essentially ensures that the learned features implicitly encode the task of mapping, motion prediction, occupancy prediction, which in turn yields better planning performance. But then online, one only needs to activate the motion planning head. And when we compare this architecture again with the UniID, what we saw is similar or even better performance, but at a much higher compute efficiency. So basically, we can run this at 26 FPS as opposed to 6 FPS. And the reason being is that online we only exercise the motion planning head. Now, importantly, this architecture that can be end-to-end optimized retains introspection and interpretability properties, since some of the heads can be optionally exercised, like, for example, motion prediction or mapping. Either online, you can exercise them at a lower frequency, for example, for runtime monitoring, or offline, just for debugging purposes. So importantly, ParaDrive is designed from the ground up to integrate foundation models. And to integrate them, I would say, in a surgical way. You can certainly think of replacing a whole stack with a foundation model, and that's possible, and we're investigating that as well. But this architecture actually allows you to integrate foundation models in more targeted ways. For example, we can use foundation models in the input space by providing new, more powerful input representations, for example, those generated by video prediction models, which is a separate line of work that I won't be presenting today because of lack of time, but that is an important part of our research program. Or indirectly, foundation models can be used to shape input representations via strongly regularizing tasks, like, for example, that of computing generative word models. And finally, foundation models can be used in lockstep with the motion planning head at training time, for example, by providing value function to ground the planning head in semantic reasoning, or online, as I will discuss later, to provide runtime monitoring capabilities. A very simple use case, for example, could be to use a large language model as a navigation planner to help the motion planning head, which is actually what we're doing in the current work that is under preparation, where we use literally a large language model to help with the navigation planning task. So basically deciding how to navigate around construction zones or change lane. And, I mean, this is something that you can do with classical methods. Typically, it tends to be quite painful because it's, a lot of case by case and it's a bit brittle. It was encouraging to see that actually we can do this almost seamlessly with a large language model. For example, a case whereby the route planner asks the vehicle to turn right ahead, but the large language model serves the purposes of a navigation planner. Reason about the scenes is that there is a vehicle, the one in the green box next to the ego vehicle, and so provides the action of staying in lane until the situation clears, and then the vehicle can move right. Now, what's the big deal here? You can do this classically. The point here is that this was done almost for free just by using large language model. And you can do also more intricate cases, like, for example, this is the handling of a construction zone with the cones. The route plan basically asks the motion planner to turn right. The behavioral planner, powered by the large language model, reasons about the scenes, and then act accordingly. So this is just to say that there are many different opportunities to use foundation models in a stack. A parallel architecture seems to be a very promising architectural archetype to inject foundation models, and you can inject them in many different ways. The jury is still out in terms of which foundation model is best. In my mind, there are two main pre-training tasks: that of video generation, that leads to video prediction models, and that of text generation, which leads to large language models. Arguably, video prediction models might provide the ultimate word model, so we can use the input space. Large language model might provide the ultimate reasoning engine. since reasoning is encoded in a way in language. And of course, I also see a lot of opportunities for blending both video prediction model and large language model. I want to conclude with a little bit of discussion about safety. Of course, there are a lot of concerns about using such models in the stack, in the online stack. But as I said, they're not black magic. They're just data-driven models. And of course, we're looking at several different techniques to keep this model in checks, including works on uncertainty quantification, adding guardrails, coming up with testing regimens in order to empirically verify these models. And I could spend an entire talk about it. But what I want to discuss is actually how we can use these models to improve the safety of a vehicle. And you can do it, and you can use them in different ways. Again, you can use them as runtime monitors online or offline, for example, as a safety evaluator to really spin a data flywheel in terms of how you improve a stack. I want to talk a little bit about the topic of runtime monitoring. This is something that actually I mentioned last time I visited here several months ago, and I'm going to provide you an update. So specifically, the starting point is this video from Tesla. As you can see, there is an endless stream of traffic lights. That doesn't make any sense. But now you see what is happening. So basically, there is a truck that is transporting traffic lights that are detected by the detector as legal traffic lights. And so basically, the Tesla vehicle enacts a ghost brake, which is an inconvenience, but also a safety hazard. And this is another case whereby there is a stop sign that is printed on a billboard. Again, it's interpreted as a legal traffic sign. And so this poor customer, Andy Whitman, had the issue that to go home, every time I had to drive in front of this billboard, and the Tesla vehicle was slamming on the brakes. So what is interesting about these examples is that you cannot really say that the detection algorithm, for example, has been malfunctioning. These are anomalies that are due to a very tricky and unusual combination of in-distributional events that jointly provide an out-of-distribution scenario. And I refer to these anomalies as semantic anomalies. Of course, these are very difficult to reason about, at the design stage. But the point is that, of course, all that a vehicle needs is a little bit more contextual and semantic understanding to reason about these edge cases. And so how we can add this semantic understanding to a vehicle? Again, with foundation models. Specifically, we'll be looking at how we can leverage large language models to reason about semantic anomalies. To illustrate this point, so we have recreated the previous case in Carla. So there is a truck that is carrying a traffic light. And then we have explored the idea of using a general purpose open vocabulary object detector to parse the scene. And the detector, among other things, it finds that there is a truck that is carrying a traffic light. And then we use this information with an input prompt template, which describes the task, as well as a few short examples informing the large language model about what factors to consider when detecting anomalies. And then what we receive as an output is kind of interesting. So for some elements of the scene, like a tree, those elements are classified as normal. But, for example, for the case of the truck, the traffic light, that is classified as anomalous. It is also interesting that the explanation that is provided is kind of reasonable. So the model said this could deceive the vehicle into interpreting the traffic light as a legal traffic signal. It's kind of interesting. And another is actually a lot of work, very interesting in seeing how these large language models provide a level of explainability for a decision-making step. And this is one of the stantiations of that idea. So we have a paper with a lot of baselines and comparisons. But one drawback, or at least one weakness of this work, is that in order to reason about anomalies, we have to get the fully autoregressively decoded output, which can be extremely slow. And it is bad because runtime monitors are basically baggage. It's something that you have in addition to your stack. So by definition, it should be very lightweight, very quick. It should have a minimal computational footprint. So the question is, how do we make this a bit more actionable? And the key technical insight here is that oftentimes detecting if there is an anomaly is a task that is easier than the reasoning about that anomaly. So we wonder whether maybe we could use the LLM embeddings directly to detect an anomaly. And then if an anomaly is detected, then use the fully autoregressively decoded output to reason about that anomaly. So that in most situations, since we only reason in terms of LLM embeddings, we can actually have a very minimal computational footprint. And then when there is something that is detected as bad that we have to reason about, then okay, we query the full model, and maybe we had to slow down a little bit, but that would be quite rare. And in a sense, it is similar to how a human drives. So typically, you don't really pay attention to what you do. But when there is something very weird, then you slow down and you start thinking about what you should do. Well, but how do you do all of that? Well, the idea here is to use an LLM to compute the embeddings from the AV prior experiences. And these embeddings are stored into a vector database. Then for new observations that come in online, we can compare these embeddings, so the embeddings that have been computed online, against the stored embeddings. And then compute the similarity score, depicted here as S. If this dissimilarity score is too large, then we deem this scenario as anomalous. So the idea is relatively straightforward. Here, ET is the embedding that is computed in real time, say at the 10 FPS, and the EIs are all the embeddings that have been pre-computed at the design stage and stored in a vectorized database. So what is neat about this approach is that the LLM embeddings still have some level of contextual understanding that is useful in order to capture complicated anomalies, but they do not require the full decoded output of a large language model. Then if something is detected as anomalous, then at that point we decoded the full output and we think about what to do. So let's see how this actually works. So on the left-hand side, I'm showing, again in Carla, a classical stack with no LLM reasoner. There is our stop sign on a billboard. It is detected as a legal stop sign, so the vehicle stops. On the right, we have this embedding-based anomaly detector that is detecting that the stop sign on the billboard is something weird. Then we slow down to reason about the situation. The LLM says that there is no reason to worry about, and then we keep going. And importantly, we can run, so for the embeddings, we use a model called MPNet, and we can actually run this model very fast. So basically on an AGX Orient, the latency is about 0.05 seconds. And then for the full-blown model, actually we use GPT 3.5 Turbo, which is slower. It requires about 3.8 seconds in order to reason about the scene. So we embed the anomaly detector plus runtime monitor into an MPC control scheme, where we also take into account the delay that we would incur by querying a large language model, so that we always keep contingency plans feasible. And then you have this kind of emerging behavior whereby the vehicle naturally slows down to buy time in case you want to query fully a large language model. And then again, this idea of a fast flow reasoning or multi-frequency reasoning comes back, whereby you only use these models when you really need them. If you just want to go straight, you don't need a large language model or a vision language model. You only use them when you need them, and in a way that is also compatible with the safety constraints, for example, keeping contingency plans always feasible. Yeah.
Mm-hmm. Yeah, the question is how scalable is this approach? Because we still need inside our database the set of like anomalies.
Not all anomalies, actually. By definition, we don't have a database of anomalies. What we have is a database of nominal experiences. That said, of course, the data set of nominal experiences can be very large. Now, the data set of nominal experiences in principle is not too hard to build. Like, for example, if you want to certify an automated emergency braking system, you already have X thousands of hours in order to compute your mean time between failure, then it becomes your database. But that database can become very large. So actually what we're currently working on is how you take this large, and of course there is also a lot of research in the machine learning community about it, how you take such a large database and you distill it down to the nominal experiences that are most representative. So that's an excellent question. We haven't done that part yet. So there are two aspects, how you build a database and then how you distill it down. Within a database, if you are in an AV company, it's not too hard in principle. But how you make it actionable through, by basically reducing it in a principled fashion, that is something we're working on.
Based approaches.
What's that?
I'm actually learning based approaches probably.
Yeah, exactly. No, that's what I'm saying. The good news is that there is a lot of work. I mean, it's not that we are the first one to try to take a big database and make it smaller, right? Here, of course, the little bit the challenge is that you want to do it in a task-driven way, so that basically you get good closed-loop performance. So you ideally don't want to read only in terms of open-loop metrics. All right. So okay, here just one example, a non-AV application. This just was to show that we can run all of this in real time. So we implemented on a quadrotor as like a toy experiment. We want to show that this is real time compatible. So the task is to land on the box with the red pad. All of these objects have been seen. There is an object though, the keyboard, that is out of distribution. It's never been seen, and so the quadrotor doesn't know if it's like a missile that can shoot down the quadrotor or not. So it is flagged as something that is out of distribution. And then we query the GPT 3.5 in this case, and basically say that the keyboards cannot kill quadrotor, so we keep going. Anyway, so, so takeaways, why foundation models? Again, we don't want to use them just for the sake of it, but I think they provide key opportunities, particularly through the lens of their long-tail generalization capabilities. A key important point for me is that they provide opportunities to empower the full AV program. The software on the car, for sure, but there are many other opportunities in terms of auto-labeling pipelines, simulation, automated evaluations, data flywheels, data generation, if you're using, I don't know, reinforcement learning or whatever. There are many types of foundation models, obviously, depending on which task you use for pre-training, primarily. Text generation and video generation being the two predominant models. Actually, we're working with both models, and opportunities abound in terms of specialization and unification. In terms of using foundation models for autonomous vehicles, you can use them to both replace existing pipelines, for example, navigation planners, or to improve them. And a parallel architecture provides key opportunities to embed foundation models in a surgical way, particularly through the notion of fast, low reasoning, whereby maybe some of the heads, for example, LLMs, could be exercised at a slower frequency on demand. And actually, there are a few companies that are already looking at this idea. In terms of simply using them, of course, we had to do some work, particularly in terms of guardrailing them. But I think that is feasible. But second of all, they also provide the opportunities to improve the safety of an AV stack, for example, by providing opportunity to design better runtime monitors. Of course, huge thanks to both my students at Stanford and NVIDIA. And I said it was going to take 35 minutes. It took actually 40 minutes. But I hope it was useful.
Yeah, let us thank the speaker.
Thank you.